Okay, now we're going to move back to the first one. Now, we did it in this order because this one is a little bit trickier. If you remember with the tension problems, if you were given two cables and you knew the tension in one of them, you could solve the whole thing just using trigonometry and components. But if you were in a situation where you were just given the mass of the object that was hanging from the two, and you were supposed to figure out what the tension was in each wire, then you ended up having to use a system of equations to do it. And we're going to find ourselves in the same situation here. So what you're looking for with these type of problems is, do I have the total x and y momentums at the beginning, right? And so then if you're looking for something at the end, if you have the x and y momentums, or if you can find the x and y momentums at the beginning, then you have the x and y momentums that you need at the end, and then solving it is somewhat straightforward, with practice, of course. But if you don't have a way of actually solving for the momentums at the beginning, then it gets a little bit more complicated. So our situation here is that you have a billiard ball moving toward a stationary billiard ball. They collide, and then they move off in a northeast and a southeast direction. Okay, and so we get this kind of situation going on. So let's go before. So you have ball, we're going to call this ball A and B. Okay, it's going to make it a little bit easier. Okay, so instead of billiard ball number 1, we're going to call that billiard ball A. Oh boy, that's terrible. Let me try this again. And instead of billiard ball 2, we're going to call it B. It's just going to make our notation a little bit easier. That's all. Okay, so we have billiard ball A. It's traveling east, this direction, toward billiard ball B. So here's billiard ball B. Now I drew it upward a little bit because A is going to strike B, and then they're going to move off in those directions. Okay. Now, in the after section, so after collision, now it says that they are observed to move off at 45 degrees, A in the northeast direction and B in the southeast direction. So I actually drew this the wrong way. A should be glancing off the top of B and not the bottom of B. But, we'll fix it now. So at the end, you've got ball A. Yeah, ball A is moving in the northeast direction, like that. And ball B is moving off in the southeast direction, like that. Okay, and if we look at their components, we can say, just like in the previous one, that the x components, the x momentums at the end, have to be equal to the x momentums that were there at the beginning. And the y momentums at the end have to be equal to the y momentums there were at the beginning as well. Okay, so now we're going to look at what was happening at the beginning. What were the momentums that were there at the beginning? Okay, so first of all, writing down our inventory of things that we know, it does not tell us their masses. Okay, so M1, or rather MA, we don't know, but it does say that they are equal masses. So instead of writing MA and MB, we're just going to write that MA is equal to just mass. Okay, so rather than writing MA and MB all the time, we're going to just say that these are both the same thing and they're both M. Okay, so we're going to have a whole bunch of variables, just like in the tension one that we did in the dynamics unit. We're going to have a bunch of variables, and the problem is that we have too many to actually solve for any of them. So if we can reduce the variables, that's going to make this easier. Okay, so VA A, that's a really big V. VA is 3 meters per second. And VB is 0. Okay, now I haven't written the x's or y's in here because there's no y motion at all at the beginning, and so all of this is just going to be x stuff. So this is VAX, but since B isn't moving and there's no VAY, I'm just not going to bother writing that in here. Okay, so there's a couple things that we can do from here. We're going to look at what's happening in the y direction and what's happening in the x direction. So let's start with y. It doesn't matter, you can start with whichever one you want, but I'm just going to start with y. So in the y direction, the momentum at the beginning is equal to the momentum at the end. So the y momentums at the beginning have to equal the y momentums at the end. So at the beginning, there is no y momentum, right? Ball A is just moving horizontally, ball B is not moving at all, and so at the very beginning, there is no y momentum, 0 kilogram meters per second. Okay, at the end though, each ball has momentum, just in the opposite direction. So we have ball A, let's go P, A, Y, minus P, B, Y. Okay, so this is saying we know they're going opposite directions. This one's going north, this one's going south. It told us that in the question. So I've put the direction of that vector in here already. Okay, so the momentum of the first ball in the ball A in the y direction is going to be equal to the momentum of ball B in the y direction. Okay, so then we can just go like this. M, so total mass, or the mass of each of them, the mass times the velocity of ball B in the y direction is equal to the mass times the velocity of ball A in the y direction. Okay? But notice that we have a common mass here, so we don't even need that thing. So what this says here is that the velocity of ball A and the velocity of ball B should be the same, just in opposite directions. Okay, so that's going to be important. Now we're going to do the same thing for x here. X. Okay, but in this case there is momentum at the beginning. So we're looking for what are all the momentums in the x direction at the beginning. It's really only ball A's momentum. Okay, so we're saying the momentum of ball A in the x direction, I'm going to put an x in there, equals the momentum, oh no, I wanted to make this a 1, not an x. Okay, the momentum of ball A at the beginning is equal to the momentum of ball A at the end plus the momentum of ball B at the end. Okay, and we're talking about the x direction. So you have to keep in your head all of this stuff is x component stuff. Okay, so the momentum of ball A at the beginning. And here's where the trouble comes in. We don't know the momentum of ball A at the beginning, right? We know its velocity, but we don't know its mass. So what we end up with is that mass times 3, I'm not going to put in the units in all of this stuff because it's going to take up way too much space. So mass times 3, that's the momentum of ball A at the beginning, is equal to the momentum of ball A at the end. So that's mass times we don't know what. This is where we're going to have to do some trig. Okay, so we need the x velocity of A at the end. Okay, so let's just go back up here. The x velocity of A, right over here, so this is VAX, this is VBX, this is VBY, this is VAY. So this would be total VA, or VA2 because we're talking about at the end, and this is total VB. So just like we did in tension, at this point what we're going to do is go VAX is equal to VA times the cosine of 45 degrees. Okay, you see where this is going. We're going to make this list. VAY is equal to VA times the sine of 45 degrees. Okay, VBX is equal to VB times the, what am I doing now? Cosine. Cosine of 45 degrees. And VBY is equal to VB times the sine of 45 degrees. Degrees. Okay. Now, like this one's a little bit easier than it could be because they chose 45 degrees in the example. Okay, and we know 45 degrees means the x component and the y component are going to be the same. So really, this VA cosine 45 and this VA sine 45, they're going to be the same, and so it's going to make the math a little bit easier, but you should be able to do it even if they aren't the same. So I'm going to do this question as though I'm expecting them not to be the same, so that's hopefully going to be helpful for different kinds of problems. Okay, so the velocity that we're putting in here for ball A at the end is the x velocity. So that's VA cosine 45. And the momentum of ball B at the end is m times VB cosine 45. Okay, again, this could be easier because of the 45 degrees. This component and this component are actually the same thing, but let's pretend we don't know that. Okay, but what we can do, looking at this equation, I see mass in every term. So I can cancel out that mass everywhere, and now I've got a somewhat simpler equation here. Okay, but I still have two variables in here that I can't solve for either of them. Again, ignoring the fact that we know they're the same. So I'm going to go back up here, and I know that VBY and VAY are the same. That's what this equation says. Now, again, because it's 45 degrees, we also knew that, but again, pretending we don't. So we're going to put in our component formulas here. So VBY is, I'm going to move this up here just for some extra space. So VBY is VB sine 45 is equal to VAY, which is VA sine 45. Okay, so I'm going to replace VB in the other equation. So let's get VB by itself. VB is equal to VA sine 45 over sine 45. So they cancel out. And again, it's because of the 45 degrees thing. But there could be situations where they don't just glance off equally at 45 degrees, where they glance off at different angles. And so then you'll need to be able to do the whole thing rather than shortcut it down to where we're about to shortcut it. So we cancel them out, and what we end up with is VB equals VA. So the total velocity of each is going to be the same. VB equals VA. Okay, they have the same velocity. They are going off in different directions, and so that's taken care of by the fact that we've put negatives in place over here. We've already said what direction things are happening in, so we don't need to worry about the fact that these are actually not the same direction. Right now, we're just talking about the magnitude. Okay, now we can use this in our, oh boy, we can use this in our other formula down here, just like we did with the tension questions. Okay, so now we know that 3 equals VA cosine 45 plus VA cosine 45. Okay, so this is just 2 VA cosine 45, right? So we can put together these two variables because they have the same coefficient, or it doesn't really matter if they have the same coefficient. We can put together their coefficients because they're the same variables, right? So VA cosine 45 plus VA cosine 45 is just 2 times VA cosine 45. And so what we end up with is 3 over 2 times the cosine of 45 equals velocity of ball A. That's at the end. We're talking about at the end of the thing. Okay? And what you end up with when you do 3 divided by the cosine of 45 is 2.1 meters per second. So VA is 2.1 meters per second. And then we also know that VB is the same, 2.1 meters per second. Now, these are supposed to be velocities, so they should have directions on them as well. It tells us what the directions are in the question. So we don't really need to worry too much about that. But in case it really bothers you, VA is east, 45 degrees north. And VB is east, 45 degrees south. And that's the whole thing. Now, again, this one is simpler because we have that 45-degree angle going on. But if it were a different angle, you could still use this exact same method to get to the final velocities. It's just that in this particular step right over here, we wouldn't cancel out the sine 45 over sine 45. They'd be different angles. So no canceling out there. The substitution still happens. It's just that it's a little bit more complicated. But you've already done that in the tension section. So I think you're going to be okay.